Okay, good morning everybody. I hope everyone's having a wonderful day. So before anything, I just want to give you a quick reminder. Remember, assignment 3 is due by the end of October 31st. The 8:30 rule is still in effect so that you can submit up until the next morning, until 8:30 in that morning. So boo, Halloween, fun. So anyways, I recommend, it isn't going to be that long of an assignment, so I recommend just drilling it down, just getting it done, get it out of the way if you can. Just be careful, because as with implementing most data structures that involve careful operations, make sure you carefully look at what the pseudocode tells you, and make sure you understand it carefully and based on what we've seen in class. So other than that, I am just about done marking the midterms, so I'm hoping to have those back for you by Wednesday. If not, it will be by the end of Wednesday. I will be putting up a solution for this midterm, so I'll let you know when that comes out, and I'll be getting that done as soon as I can. I would have had it done sooner, but it's sort of one of those things where a couple things came up over the weekend. So anyways, I wanted to pick up from where we were last day, and I was starting to introduce what is called depth-first search. Now, as just a reminder, in depth-first search, I want you to think of the graph more like a maze, where I want to explore this graph. So when we think about this maze, I want you to think about the vertices as intersections and dead ends in this maze. So just imagine I give you this graph over here, and just imagine it's like this lurky, scary dungeon that you go into, and you're trying to figure out your way through and trying to explore it. So those are the vertices. There are these intersections. So they can meet at corridors or they're dead ends, like H, for example, to dead end. And then the edges are just going to be passages that connect them. So last day I brought up this idea that, okay, well, in the Greek myth, Theseus and the Minotaur, what happens is King Minos' daughter, Ariadne, gives Theseus a ball of thread to help get through and explore the maze so that Theseus doesn't get lost. Because this maze, the labyrinth, is very, very complicated. Like, so complicated people don't find any way of escaping it. And there's unfortunately a really, really spooky monster in there. Well, it's a very misunderstood monster. It's called the Minotaur, a half man, half bull. We're not going to talk more about the backstory of that. I talked about that last day. But I want to really talk about depth-first search in relation to this. So first, we're going to imagine that Theseus enters into the labyrinth, say right here at A. And Theseus is going to reveal more and more of this labyrinth by leaving some of the thread so that Theseus can come back if, say, Theseus hits a dead end and finds no other options to proceed to explore the labyrinth. And as Theseus is going to do this, Theseus is going to mark a vertex and then is also going to label an edge if Theseus travels across that edge. So remember last day I told you we're going to make the assumption that the vertices and edges can be marked and labeled in constant time, which is something you can quite easily do, as I discussed last day. And whenever Theseus, like I said, hits a dead end, Theseus is going to retrace steps and revisit more options to explore. And this mechanism of the thread is going to be recursion. So the string is going to end up being what's going to be represented as our call stack. So I want to walk through this idea by connecting it with what we said before. So what I'm going to do is I'm going to have it's so that Theseus is going to explore this labyrinth. Now, unfortunately, we're going to look at it a little bit easier. I'm just going to allow Theseus to explore the labyrinth without a Minotaur in there. And so just to be a little bit more G-rated here. So what I'm going to do is I'm going to start off by having Theseus enter into the labyrinth. And that means that I'm going to start off at vertex A as U. And I want to reach every vertex that is reachable from U. So when I start this off, Theseus is going to mark this corridor or this intersection. It's going to label A. We're going to mark it I'm going to always mark vertices. I'm going to label edges. So I'm just going to try to be consistent when I say this stuff. So I'm going to start by marking A, and then I'm going to proceed down one of the hallways or corridors. And so, for example, what I could do next is I could try to proceed to H. So what I'm going to do is I'm going to take my thread. I'm going to, well, now I'm Theseus all of a sudden. Believe me, I'm not that jacked. I'm going to spool out some more of the thread to get to H. So when I go across H, I'm going to label H, because this is the first time I've encountered this corridor, because I've never been to H before. So now what I do is I'm going to now visit H. So the first thing I'm going to do is I'm going to mark H, and then I'm going to see if there's any more places I can explore from H. Well, unfortunately, there are none. So what I'm going to do is, okay, well, I'm going to retrace my steps. I'm going to roll back up the string that I have, and I'm going to go back to A. So I'm going to be done at H. I'm going to go back to A. Then I see, okay, are there any other passages I can take? So notice I can go to B. So I'm going to go unroll my string, and I'm going to go to B. Then what I'm going to do is I'm going to now consider the intersection B. I'm going to mark B because, hey, look, I got the B. And then what I'm going to do is I'm going to consider one of these pathways that I found. So notice that there's more than one. So in this case, I'm going to pick just one of them. I'm going to go to C. So I'm going to label this edge right here with the blue, because this is the first time I'm encountering C. I've never seen C before. I would know because it's marked. Sorry, if it would be marked, I've already been to it. If it's not marked, then I haven't been to it, right? That's an very easy way I can know where it is. So now naturally, okay, I'm not done with B yet. Remember, I went down B, now I'm over at C. So now I'm going to go visit C. I'm going to mark it. Then I'm going to look and see if there's any passages I can continue to explore down. In this case, I have one edge that I can explore, right? So I'm going to go down this edge here, down to D. Then I'm going to go visit D. So first thing I'm going to do is I'm going to mark D. And now I'm going to consider all the passages that I could possibly go to. So let's take a look. Let's see. Well, what's the first one I haven't labeled yet? It's this one. So I better go down this way and say, I'm going to go visit E. So I'm going to go visit E. And then I'm going to go mark it, just like I did before. Now, I'm just going to keep going. Now, I'm not going to worry so much yet about exploring the rest of this graph, except for I'm just going to keep going. I'm going to go see if I can go see F. Suppose Theseus is just really clever and just sees B over there, but we're going to assume that Theseus doesn't. We're just going to proceed anyways to F. And okay, I'm going to just say, actually, now, Theseus is going to change his mind. He's going to try to go this way, but Theseus notices quite quickly, hey, look, I've already marked B. That means I've already been there. I've already been the B, right? So what Theseus is going to do is Theseus is not going to go down that passageway, because Theseus has already been there. Instead, Theseus is just going to label this passageway with a different color. Because Theseus already knows that takes Theseus back to somewhere Theseus has already been, right? So when I'm done that, I'm just gonna, let's go this way. So Theseus is now going to go visit F. What's the first thing I do? I'm going to mark F. Well, Theseus is going to mark F. Looks for any unlabeled edge. Here's an unlabeled edge. So Theseus is going to travel across that edge and visit G. What's the first thing G does? What Theseus does when reaches G? Marks it, then looks at all of the passageways that that aren't labeled yet. Notice that there's this one right here. Question for you. Should Theseus label this edge blue or red? Red, exactly, because Theseus has already been there before, right? So, very good. We don't go down that way. Now, technically Theseus could, but Theseus wants to make sure that Theseus doesn't get lost because we need to use our ball of thread, right? So, what Theseus is now going to do is watch this. Now, this is where it gets neat. Okay, so now Theseus, remember, Theseus is at vertex G. So Theseus has all this string all the way out, and this string will allow me to work backwards all the way back to the entrance, if you look carefully at my stack. So now notice that when Theseus does this, what Theseus can do is just retrace steps by just simply unraveling, winding this thing back up. Sorry, I'm getting really excited about this. So now Theseus is done at G because now every edge has been labeled, meaning every passageway has been explored from G. So now we don't need G anymore. So we're done at G. So I wind this back up to F. So I'm just following back this way. Okay. I'm done at F. All the edges are in fact labeled. Okay, E, all the edges are labeled already. But notice that I'm following along these blue edges. So now E is done. D, all the edges have been labeled, right? And remember, I marked, right? So I'm all done. I'm all good to go. C, there's no other edges for me to label, so I'm all done there. B, oh, all the edges are in fact labeled. And now I'm back at A. Look at all of my edges, passageways, and they're all labeled, right? So I'm all done. So now Theseus has escaped the labyrinth. But now look at what Theseus has done. Theseus has labeled every edge in my graph and also has marked every vertex in this graph. So notice that every edge is labeled. Every edge is labeled. And every vertex is marked. That's supposed to say vertex. It's sort of melted. Okay. So notice that I've traversed the entire graph. Now I have a question for you. Notice that my graph is connected. If it wasn't connected, would this process, in fact, label every edge and mark every vertex if the graph isn't connected? Exactly. No, it won't. Because notice that remember, Theseus just has this ball of string here, right? That's all Theseus has. So there's no way that Theseus has a pickaxe, can bust down a wall in this dungeon or labyrinth and find a new spot to keep exploring. Theseus does not have that ability, unfortunately. Theseus only can follow down the passages and mark and label the passageways and intersections. Just like in DFS, depth first search, so that's why I'm going to refer to depth first search as DFS. In DFS, what I'm going to do every single time is really quite simple. So when I visit a vertex, I'm going to mark it, and then I'm going to consider all edges that are incident on that vertex. If the edge isn't labeled, then I better prescribe a label to it. And if I find a new place to go, which means that the vertex isn't marked, I'm going to apply DFS recursively on that vertex. So notice that when I describe DFS to you here, I've assumed that this thing starts off by providing it as DFS, where I give it U, where U is where it starts. So this is the idea of DFS. Is the idea of how we explore the graph clear to everybody? So I mark a vertex, then I if I find an edge that I have not labeled, I'm going to label it. And then if I can explore any further, I'm going to take that edge and recursively apply the process again. Okay, so I'm going to show you now the pseudocode for DFS. And we're going to do our analysis on DFS. And then after that, we're going to look at some applications of DFS. So you can look at DFS almost like a whole framework for which we could design all sorts of different graph algorithms to do all sorts of things. So over here, I have DFS. So as input for DFS, I take in a vertex that belongs to the graph, and I'm going to assume, for the sake of our discussion at this point, that this graph is indeed connected. So it means that there exists a path from each vertex to every other vertex in the graph. So that means it's going to label every vertex, and it's going to mark every vertex, and then it's going to label all the edges. That's what we can say about DFS. If it isn't the case, then you can't say that. So anyways, here's the way it works. You mark the vertex that you're at, then you consider all edges incident on you. You consider all the edges incident on you. And then what you do, so this would be like you're going to have a list of all your incident edges. And depending on how you represent the graph, the way you perform this will change. So I'll talk about that in a moment. So you're going to get each incident edge from on vertex U. And you're just going to check, is that edge labeled? If it's not labeled, then you have to check if V, the other endpoint of that edge, is marked or not. If it's marked, it's just like my case over here where I was at E and I noticed B over here. B was already marked, so I'm not going to find anything new over here. We label these as back edges. So the red edges I have here are called back edges. So these red edges here, these are called back edges. The blue edges are what we often call, I'm not going to draw arrows everywhere, otherwise I'll absolutely destroy the picture. These are often called discovery or forward edges. So sometimes I'll call them discovery edges, sometimes I'll call them forward edges. Just know that they're synonyms. So that means that they mean the same thing. So I'll call them discovery edges here in the pseudocode, but if I ever use the term forward edge, because some people like using the phrase forward edge, that's what it literally means. It's the exact same thing. So if V is marked, then you know that you've already been there before. So we label that edge a back edge. Otherwise, we found a brand new passage for Theseus to explore. This is why we call it a discovery edge. And then I recursively apply DFS on the other endpoint of the edge. So note that the way I've set this up, I've assumed that all the edges are not marked and all of them are not labeled when I start this process up. So if you're trying to do this over and over again, you have to make sure you tidy up the graph before you apply this again. So when you're done this, it's going to mark a whole bunch of vertices and it's going to label a bunch of edges. You may use this information in the future, but if you need to start it over, you have to make sure you clean up your graph afterwards. What I mean by that is you would unmark all the vertices, you'd remove the labels on all the edges. So remember, these are just going to be attributes you also augment into your object. So for example, if I have a vertex, it could be marked or unmarked. So you would just make sure this information is encoded somewhere in your graph. So I talked about that last day, if you're wondering. So let's analyze So first, does everybody understand what I mean by DFS? So I start at some vertex U, and this process will get me to every vertex that is reachable from U, assuming that the graph is connected. Is there any questions about this? Because I want to do the analysis with this, because depending on how we represent the graph, it might be a little different. Or at least the way we compute the time complexity may differ. Okay, so if there aren't any questions, let's analyze this. So note in the notes I have a little bit more of a thorough explanation of this initial setup, but I'm just going to do it like I have a couple times before. What's the first thing I do usually when I analyze a recursive algorithm? What's the first thing I usually tell you to do? What's the first thing I say? It's like, to make this easier for yourselves, I tell you to, well, not base case. Think about it. Remember, this involves recursion. Ignore the recursion. Exactly. I want you to ignore the recursion, but very close, very close. Yeah, so what we want to do is we want to ignore the recursion first, and we're going to analyze how many operations this does, and then we're going to incorporate the recursion. Fortunately for DFS, it's really easy to do this, which is great. So anyways, what I'm going to do is I'm going to isolate out different constants that are going to represent the number of operations that occur, but you're going to notice very quickly that this algorithm doesn't have a typical like if, base case, and then the recursive case. You notice everything is just, yeah, this happens, and then you check all the edges incident on it. So notice that effectively, there is no explicitly written base case here. So every time I give you some vertex, it's going to perform, our analysis is going to apply to any one vertex in the graph that this gets run on. Is that clear? So the first thing I want you to notice is that I mark a vertex. Last day I told you that we're going to assume that's going to take some constant amount of time to do. Then, if I'm ignoring the recursion, so remember I'm going to ignore the recursion. I'm going to ignore the recursion for now. That says ignore recursion, by the way. It's Monday. So anyways, so what I'm going to do now is I have all of this inside of my loop here. Notice that if I check this is not labeled, I can do that in constant time. Checking if a vertex is marked, that takes constant time. I can label this in constant time because I have access to the edge itself. I don't have to go finding it or anything. I already have access to it. And I can label, and the DFS, remember I said to ignore the recursion. So all of this is going to take some constant amount of operations. So all of this is going to be some constant number of operations, some C2 number of operations. So notice that if I'm doing my analysis, I want you to observe what happens when we bring in one other thing, this loop here. This loop is going to play a very important role in how we do the analysis here. So if I'm looking at the overall running time of this, ignoring the recursion, I better take into account this loop. So this is going to be C2 times the number of iterations of the loop. Sorry, let me see. I wrote that in red for some reason. Let's write that in black because that's a little harder to see. C2 times the number of iterations. My bad. C2 times the number of iterations, right? Because that's what this means, right? I go through each iteration of this loop and I do some constant number of operations, right? So I want you to observe that if the graph is connected, how many recursive calls are going to happen? How many are going to happen? Surely when I did this example here, remember this is just one graph. I'm talking about any graph that's connected. I'm going to assume that I visit each one of the vertices, right? So when I bring the recursion back in, how many times am I going to do all of this? It's going to be based on the number of vertices. So I'm going to look at this from a perspective of each vertex. So just to summarize, the total number of operations at a vertex, vertex U, is going to be equal to C1 plus C2 times the number of iterations. Right? C1 plus C2 times the number of iterations. That's the total number of operations that are going to happen at a given vertex. But we need to incorporate all the vertices because we need to observe. So we're going to observe that the algorithm visits every vertex in G exactly once. So we're going to need that fact. It's a very important fact. So I want to put this all together. So I'm going to move on over to the other board here to finish up the analysis here. Okay, so now I've determined how many operations are going to happen at a given vertex, but if you think about that, that means the total number of calls is the number of vertices, right? Total number of calls is the number of vertices. Number of vertices, implying the time complexity. The time complexity is the sum of C1 plus C2 times the number of iterations over all of the vertices. So I sum over each of the vertices. So this is generally what it looks like, but you're going to notice very quickly that the way I formulated this, I haven't really taken into account what this would be. It depends on how we represent the graph. Does everybody see that? So notice that when I had this loop where I checked each of the incident edges, the way we represent the graph actually changes how this is going to play out. Because remember, in an adjacency matrix, what do? You scan an entire row of the matrix, right? In an adjacency list, you just identify the entry for your list that you're wanting to index into, and you traverse across the linked list, right? For your adjacency list. So those are two different ways you can access this information, right? So that means that I'm going to have to take this and consider each representation carefully. So I'm going to consider the adjacency matrix first. I think it's the easier one of these two to analyze. Now, what happens in the worst case when I'm trying to identify all of the edges that are incident on a given vertex? So remember, I have my adjacency matrix. Imagine I have the entries in here along a row. What could happen in the worst case? What could happen? Say, for example, there's just one edge that my vertex is incident on. What happens? Well, there's kind of two things that can happen, right? Well, first, there may be no incident edges, meaning it's just sitting on its own, like there's no edges incident on it. It's just, but you have to check all the possible other vertices, right? Each column with respect to that row. But it may be the case that the entry you're looking for is way at the end of this. It's like the last entry of this whole process. That means you may have to scan the entire row in the worst case. So, to consider each edge UV, which is what we do with that loop there, right? Each edge incident on U, we must, in the worst case, traverse n entries in a row. And I'm going to mention of the matrix, right? Of the matrix. This means the number of iterations means the number of iterations of the loop is at most n, right? We know that in the very worst case, it's going to be n. So what does that mean? I'm just going to put it in there. Therefore, the worst case time complexity is, so I'm just going to substitute in where I have number iterations with n, is the sum of over all the vertices. This time, well, let's do, well, I guess it doesn't matter. Let's just make this v. V and v, c1 plus c2 times n, which of course this is c1 times n plus c2 times n squared, because remember I have n vertices, so I do this for each one of those, which of course this is big O of n squared, right? If you really want to go nitpicky, of course, you could write it's big theta of n squared. But notice it takes quadratic time, which isn't actually too bad if you think about it, because the whole matrix is it's an n by n matrix. So it kind of makes sense that if you want to explore the whole graph, you have to look at the entire matrix at some point. So it's not bad at all. Are any questions about what I did here for the adjacency matrix representation? The n squared. How do I get the n squared? Okay, so this n squared right here, this one right here. So remember, each time, so remember the number of vertices, is equal to n. So it means for each vertex, I'm going to add this. So it means every single time, I'm going to do this for each one of the vertices. If there's n of them, then surely this is going to be n times c1 plus c2 times. And if you don't really like this being here, you could easily just scratch that and just put an n right here. Does that make it a little clearer? So you just put n right here and then you distribute it through the terms here. But I'm just trying to be careful. So that's the adjacency matrix analysis. The adjacency list one is a little bit more crafty. So let me just write that out. The adjacency list. For adjacency list. Now, the great thing about the adjacency list is, remember, I have access to all of the vertices that are adjacent to my vertex. That implies I can tell you all the incident edges by just looking. I just look in my my adjacency list. I figure out what list I need to go into, so I index into that, and I can get then that linked list that I have there. That tells me all of the incident edges directly. That's the benefit of using the adjacency list. Is that you have access to that information right out of the get-go. As long as you can index into the list, you're okay. So, to consider each edge UV incident on U, we traverse a list for you, like I mean literally you, not like you. I mean you, which scans or traverses. I'll just say scans at most the degree of U elements. So when you put us all together, let me just summarize it over here on the other board here. Because remember, what's the length of one of these lists? It's the degree of that vertex. So just to summarize this, so I'm just going to do the exact same thing I just did a moment ago. Okay, let's do this. Okay, so let's do this. Therefore, Therefore, the worst case time complexity, that's its time complexity. Worst case time complexity is the sum for each one of the vertices. I'll say u in V. It's C1 plus C2 times the degree of u. That's what number of iterations is going to be, the degree of u. Which, of course, if you go through this, you see, okay, well, there's n vertices, so I know it's going to be C1 times n. Then I have now C2 times the sum over all the vertices of the degrees. Oh man, we know something about this. Remember, I told you that this is going to be a very useful property that we could use. Okay, so sorry about that. So let me see here. So for the adjacency list, I say to consider each edge incident on U, we traverse a list for U which scans at most the degree of U elements. So the big thing I just wrote on this board over here was just that in an adjacency list, to get all of the incident edges, we have to traverse the degree of U elements. So I just go through the degree of U. Sorry about that. So we know what this is. What is this? What is this? What's that? It's our friend, remember? How are you doing, buddy? What is that? What is that? Somebody tell me. If m is the number of edges, what is this? The handshaking lemma. Yes, we use the handshaking lemma. So by the handshaking lemma, remember I told you it's very useful. It's a very cute property, but it pops up every once in a while and it says, hey, I'm here. By the handshaking lemma, the sum of the degrees B, remember the degree of U is equal to 2 times M. That's what we know about the handshaking lemma, which implying C1 times N plus C2 times the sum of all the vertices, sum over all the vertices of the degree of U is equal to C1 times N plus C2 times 2M. But when you drop out all the constants, right, because I have a C1 and a C2 here and I have this 2 here, I can say which is big O of N plus M. If you, like I said, if you want, you could write big theta there. And that's the worst case time complexity of DFS for when you use an adjacency list. So the big thing I want you to observe about both of these is that they're technically both linear in the representation of the graph. So what I mean by linear in the representation of the graph, what's the size of the graph? It's based on the number of vertices and the number of edges. So this is why I'm telling you that this is a linear time algorithm for the graph, because its size is based on the number of vertices and the number of edges. So this is a linear time algorithm for a graph traversal. So DFS runs in linear time, where the input is based on N and M. There's 2 parameters here. You might also ask, oh, what about with the adjacency matrix? The same idea applies, because remember, you can always rewrite the number of edges with respect to the number of vertices. Remember, the number of edges is big O of N squared. So if I give you the number of vertices plus the number of edges, it's most certainly going to be big O of N squared. But yeah, so they don't, you get nothing too particularly different between the two. Just remember, the adjacency matrix is encoded by an n by n matrix, so it kind of makes sense why it's written that way. Is there any questions about how I got the worst case time complexity for our adjacency list? So remember, at the heart of this was using that handshaking lemma. That's your best friend. It wants to just greet you and say hi, okay? Now, I do want to make one remark, one important remark. Can we ensure DFS traverses every edge and vertex? So in its current form, the answer is no, because the graph has to be connected. There is a way to accomplish this without losing any of these time complexities I've mentioned. I have it in the notes. It's just very simple. All you do is you bootstrap DFS. So what I mean by bootstrap here is you're going to have another function or method, and it's just going to scan through all of the vertices of your graph. And whenever a vertex isn't marked, you're going to run DFS. So that's all you have to really do. So just make sure the graph is all tidied up, then do this for each one of the vertices. Let's take a look at the notes. And the answer, of course, here is yes. It runs in the same times in the worst case. You might naturally ask, Dan, why is it that it doesn't change? It's because whenever I give you any one graph, notice that if I had multiple connected components, so if I have like 2 or more, for example, the meaning it's not connected, every time I start up this process, remember I told you I'm going to scan through all the vertices in this DFS that gates a given graph. Every single time I start it up, I run DFS only on vertices that aren't marked. And then what I do is I just simply run it. But notice that the graph itself doesn't depend on the other connected components, except for the fact that, oh yeah, well, I have to scan through a row or I have to look through a given list. But notice that those aspects of the graph are actually only related to the connected components in question, with the exception of just checking if there's a vertex adjacent to it. So notice that when I do this process, it actually doesn't affect the other connected components. So when I mark a vertex, I don't mark a vertex twice. I only mark a vertex once. Likewise, I only label an edge once. But I may visit again a second time. That's when I know I put the back edge in if I see another vertex again, or I just already see one I already seen before that's already been labeled. So just to make a note, this is possible to do. And it does have the same time complexity. Just see the notes. It's a very brief thing you only have to do. And it's really simple. You can just augment this process by just adding another method or function that just calls your DFS that we had earlier on each vertex that isn't marked. Now I have a question for you. If I want to check if the graph is connected or not connected, can somebody tell me what I need to do? Well, you could try to count all the edges, but remember, the number of edges might indeed, like if you knew the number of edges in advance, sure, you could do that. But think about it. That is indeed one thing you could do, but I'll give you an even simpler approach. Okay, that's a very good suggestion, by the way. What I could do, remember, in my graph, so you check all the vertices to see if they were marked. Exactly, that's exactly what I was looking for. Is if there's a single vertex that isn't marked, remember, that's what I take advantage of when I want to explore the entire graph, assuming the graph isn't connected, is I start up DFS on an unmarked vertex. However, if I just want to know if the graph is connected or not, I just run DFS on a given vertex. So I just pick some vertex and I run DFS on it. If all the vertices are marked at the end of this process, then it's connected. But if there exists one vertex I have not marked, that means it's not connected. So I'm going to say if there is at least one unmarked vertex, G is not connected. So notice that you could use it very easily, take and run DFS on the graph. So DFS at a given vertex. It will mark vertices and label edges that are reachable from you. And then when you're done this process, you just look at the graph and you say, hey, look, is there any vertex I haven't marked yet? And if there is one, so you just scan through all the vertices and you say, hey, look, is one of these not marked? If the answer is yes, then you know it's not connected. So you could see that you could actually solve this problem in linear time with respect to the graph. So it's really nice and simple that way. So that's all I have to really say about DFS itself. Are there any questions about that? I have enough time to show you one application of a DFS before we end for today. And then when we come back, we'll see some more applications of DFS and one more graph traversal algorithm. So I want to show you one more application of DFS. So we can test connectedness of a graph using DFS. It doesn't affect the time complexity at all. It's really nice and simple. So I want to show you one more application. Whoops, I lost my eraser. That was pretty epic. My apologies if that was really loud. Okay, that was really epic. I like that. What a thing for a Monday. My apologies. Okay, I want to point out one thing before we go. I will have pseudocode for this application in the notes, so I'll encourage you to take a look at that. I want to talk about cycle detection. So one thing I want to point out to you is that suppose I give you DFS, and here's an example of a graph. Just a cute box, A, B, C, and D. And when I do DFS, I'm going to, say if I do DFS from A, so I mark vertices and I find some new edges to label. But notice that when I see a already marked vertex, but I have to label it, I label it as a back edge, right? So I would label this as a back edge. So the one thing that's nice about DFS is you can use DFS to test if there exists a cycle in the graph. So how do you know that there's a cycle in the graph? So if you label an edge as a back edge, then that implies there's a cycle in the graph. The way you get the cycle is you just take this red edge and you append it to the discovery edges that took me to get over there. So I would take A, B, C, D, and I would go back to A through this red edge. I encourage you to try taking a look at this with the first example in mind, where I could go to B. Notice that the cycle there would have been from B all the way around to, I think it was E, and then back up to B. So you can use DFS to do cycle detection. All you do is you detect if there's a back edge. If there's a back edge, then the cycle exists. So this will tell you if there's a cycle in the graph or there isn't a cycle in a graph. So this is a very simple way, for example, if you want to test if the graph has a tree or not. Sorry, if it's a tree or not. I should be more precise. So that's a neat application of DFS. When we come back, I'm going to show you how you can compute paths using DFS. So that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.